Hey there and welcome. So, if you've ever stared at a higher order differential equation and just felt, well, a little intimidated, you have come to the right place. Today, we're going to break down a super clear step-by-step method to solve these things. Let's get right into it. All right, take a look at this beast. It's a third-order linear homogeneous differential equation with constant coefficients. Phew! Look, that's just a mouthful for saying all the derivatives are kind of just added up, the numbers in front of them are simple constants, and the whole thing equals zero. It looks pretty gnarly, right? But what if I told you we could crack this entire thing wide open with one surprisingly simple trick from algebra? That's it. That's the secret. We're going to transform this messy calculus problem into a straightforward algebra problem. And it all hinges on one single educated guess. Think of it like a master key that just unlocks the whole puzzle. So what is this magic guess? It's the function y equals e to the power of rt. I know, it seems random, but trust me, by assuming our solution looks something like this, we can plug it back into the original equation and just watch the calculus completely melt away. You know, this is one of the coolest ideas in math, turning a hard problem you can't solve into an easier one you totally can. So, when we make that substitution, what we end up with is something called the characteristic polynomial. And here's the most important part. We've just turned a differential equation problem into a problem of finding the roots of a polynomial. And hey, we've been doing that since algebra class. Thanks to the fundamental theorem of algebra, we know that an nth degree polynomial is going to have exactly n roots. We just have to find them. So let's just break that process down one more time. You start with your differential equation. You make that golden guess, y equals e to the rt. You substitute it in, and what happens is that the derivatives just magically become powers of r. What you're left with is a clean, simple polynomial all ready for you to solve. Okay, so you've got your polynomial, and you find its roots. Now what? What do you actually do with them? Well, it turns out that depending on the type of roots you find, you'll use one of three different forms for your solution. I like to think of them as three different decoder rings for translating your roots back into the final answer. And here they are, our three cases. Seriously, this slide is your roadmap. It's your cheat sheet for everything. If your roots are real numbers and all different, you use that first form. If you get a root that's repeated, you have to start multiplying by t. And if you get those complex conjugate roots, you know, the ones with I in them, they create these beautiful sine and cosine terms. We're about to see every single one of these in action. All right, theory's great and all, but let's make this real. We're going to walk through three different examples, and each one is going to showcase one of these specific scenarios. That way, you'll see exactly how to use the rules from that table we just saw. Okay, let's go back to that very first problem we saw. Based on our new method, the first thing we've got to do is write down its characteristic polynomial. It's easy. The third derivative, y triple prime, just becomes r cubed, and the first derivative, y prime, becomes r. That's it. And look at that, it's just an algebra problem now. We can factor out an r right away. And then we're left with r squared minus 4, which hopefully you recognize as a difference of squares. And bam, that gives us three distinct real roots, 0, 2, and negative 2. This is a perfect example of our case number 1. So now we just plug those roots into our first decoder ring formula. The root 0 gives us e to the 0, which is just 1, so that's our constant, c1. The root 2 gives us c2 times e to the 2t, and the root negative 2 gives us c3 times e to the negative 2t. We just add them all up with some arbitrary constants, and that's our general solution. Done. All right, ready for example number 2? This time, it's a fourth-order equation. The characteristic polynomial is, again, pretty simple to write down. R to the fourth minus 1 equals 0. Let's see what kind of roots this one's going to spit out. So we can factor this as a difference of squares not once but twice. The r squared minus 1 part gives us our real roots, 1 and negative 1. No problem. But that r squared plus 1 part, that gives us our complex conjugate roots, plus and minus I. So this problem is actually a mix of our first two cases. And this is a really great example of how we can combine the different solution forms. The real roots, 1 and negative 1, they give us our normal exponential terms. Now, for the complex roots, plus or minus I, the real part, alpha, is 0, and the imaginary part, beta, is 1. So when we plug that into our formula from the table, we get our cosine and sine terms. Perfect! Okay, for our last example, let's look at a characteristic polynomial that's already factored for us. Now this one is a bit tricky. We know the roots of r squared plus 1 are plus or minus I, but because that whole term is squared, it means those roots are repeated. We say they each have a multiplicity of 2. So how in the world do we handle that? Well, the first pair of roots, plus or minus I, gives us our standard solution, c1 cosine t plus c2 sine t. Easy enough. But for the repeated pair, we just have to apply our special rule. We just multiply those exact same solutions by t. That gives us c3t cosine t and c4t sine t. And you know what's really cool? There's a fascinating connection here to the real world. This exact mathematical form, where you have a t multiplying the sine and cosine, it actually describes the physical phenomenon of resonance. Think about pushing a kid on a swing higher and higher with perfectly timed pushes. The math is literally predicting reality. How cool is that? Okay, let's zoom out for a second and just review the code we've cracked, because that's really what this is. Mastering this process is all about following a clear set of steps and knowing which decoder ring to pull out for the roots you find. So here it is, the whole process in 5 simple steps. It always starts with that guess, y equals e to the rt. That leads you to the polynomial. Then you find all the roots, match them up with the right solution form from our table, and then you just add all the pieces together. It's a powerful, repeatable method that works every time. And hey, if you really want to master this and not lose points on an exam, you have to be aware of the common traps. The absolute #1 mistake people make is forgetting to add those extra t terms for repeated roots. It's so easy to forget. Also, just be super careful with your algebra when you're factoring, and always double check that you found the right number of roots for your equation's degree. So there you have it. You've now mastered finding the general solution, which is pretty amazing. It represents a whole family of functions that solve the equation. But what happens when someone gives you initial conditions, and you have to find the one single specific solution that fits? Well, my friends, that is the next piece of the puzzle.